The FluidFlow 3 two-phase module allows you to model both constant and changing quality two-phase piping systems. This is an example of a two-phase system with changing quality. This means that the vapor mass fraction is not constant and there is mass transfer between the fluid phases. We can see this if we select any pipe or component on this system. If we select pipe -1 and view the results, we can see that the inlet vapor quality is 0.18, whereas the outlet quality is 0.1848. Again, if we select pipe -3, we can see the inlet vapor quality is 0.189, which increases to 0.1956. This change in quality arises from the pressure dropping as the fluid flows down the pipe, and as such, some of the liquid boils off to form more vapor, also known as flashing. If we look at the heat exchanger, we are adding some 30 kilowatts of heat to the system. This has the effect of vaporizing additional liquid. The result is the vapor quality increases from 0.1982 to 0.4606. FluidFlow also allows you to view the flow pattern map for a given pipeline. For instance, if we select pipe -1 and on the Chart tab select the flow pattern map, we can see that the flow pattern for this pipe is just on the border of the stratified wavy flow regime. If we select the following pipe, which is an inclined pipe, changing from an elevation of 6 meters to 12 meters, we can see that the flow pattern is now annular mist. This is because the gas superficial velocity has increased as a result of the pipe inclination. A quick check on the Results tab should confirm this. We can see here that the superficial gas velocity for the pipe -1 is around 8.4 meters per second. In the second pipe, it has increased to 8.79 meters per second. This is an example of a two-phase flow system with constant quality. This means that the vapor mass fraction is constant and there is no mass transfer between the phases. This model shows two fixed flows, one water and one air, combining, being heated by 30 degrees across the heat exchanger and then flowing to a separator vessel. The red dot on the separator vessel represents the liquid outlet and the yellow dot represents the vapor outlet. In this model, both pipes -6 and -3 are identical. Both pipes are 60 meters in length and 50 millimeters in diameter. However, we can see that the friction loss for the first pipe is 146,189 pascals, whereas for the second pipe it has increased and it's 198,528 pascals. This is because the gas volume, velocity, as well as other fluid properties have changed with the increase in temperature across the heat exchanger. You can get a feel for the differences by displaying the Beggs-Brill flow pattern map. We can see here that the flow pattern for the first pipe is in the intermittent region, which is plug or slug flow. And if we look at the second pipe, we can see that we are now in the distributed region, which is more like bubble or mist. These changes in fluid characteristics will therefore have an effect on the calculated pressure loss in the respective pipelines. FluidFlow also allows you to select from a range of two-phase pressure loss correlations, which can be seen by selecting Options, Calculation and the Two-Phase tab. Now we just select the drop-down menu. This final model shows how FluidFlow can automatically detect changes in fluid phase state and apply the appropriate pressure loss correlation. In this case, we have two system inlet points, both of which are defined as water at a pressure of 377 kPa(g) and a temperature of 149 degrees C. If we view the results for the pipes upstream of the ball valve, we can see that the fluid is in the liquid phase, and the software has automatically applied the Darcy pressure loss correlation. However, as the fluid crosses the valve, flashing occurs and the fluid changes to two-phase. FluidFlow has therefore applied the appropriate loss correlation, in this case the Friedel correlation, as this is what we have set from Options, Calculation and Two-Phase.